Hello everyone. In this video we will continue to examine the concept of electric fields in topic 5.1 electric fields. So, quick reminder, the most important thing to understand about electric field is what is happening. Okay? The definition is important and will be super useful later on, but the definition really doesn't convey what the point of the idea is and what it does. And so here's what we say about electric fields. We say charges affect the space around them by producing and affecting what is called the electric field around them. And the electric field is an invisible field in space that can only be seen by what it does. And what it does is produce the electric force on other charges that we initially thought was only due to Coulomb's law. Another way of thinking about this is that electric field is sort of an intermediary in Coulomb's law. The electric field is the answer to the question, how do charges produce forces on other charges at a distance? Okay, so we want to keep that in mind. And the important thing to recognize is that the electric field is going to have both a magnitude and a direction at every single point in space. So it will have both a size and a direction here and here and here and here and here, and too many points to show all of them. Okay. So let us examine, just for simplicity's sake, and to have a way in, the electric field of a single point charge. Okay, so what does a single positive charge, this red one right here, do to the space around it? Okay, what kind of electric field does it produce? And moreover, how do we calculate it? Because this field is very real and has a very particular value. Okay. So what force would a small positive imaginary charge feel placed at this particular point, a distance r away from the positive charge? Well, we already know what the answer to that question is. We know what that force would be. It's Coulomb's law. Okay, and Coulomb's law says that the electric force, that green force, is equal to K times Q. I'm going to use capital Q to indicate our source of field here. Little q, that's our imaginary point charge, okay? So what would it feel if it were there? Divided by r squared, that's the difference away, r hat. So that's what the electric force would be on the small positive test charge placed right there. So how do we calculate the electric field? Well, we use our definition here. The electric field is defined to be the limit as q goes to 0 of Fe over a little q. Okay, so we're taking this small quite seriously. If you haven't seen limits yet, you can just ignore this bit for now. It's okay. But strictly speaking, that limit should be there. And therefore, we substitute in Coulomb's law for that electric force, because that is the electric force that the small positive test charge would feel if placed at that point. So we plug that in, but remember, it's per unit charge. That's why we're dividing by this q here. So the little q's cancel, and we can see that the size of the small positive test charge doesn't matter, which is good. That's important. Remember, this is the field only due to this big positive guy, not due to anything else. Okay, so whatever we imagine to be there shouldn't matter. And indeed it doesn't. These little q's cancel, and you get that the electric field due to a single point charge is K times Q divided by r squared r hat. This looks very similar to Coulomb's law, but it has one important difference, which is the lack of that small charge. And this is a formula. This formula tells us how to calculate the field at any point around this small positive test charge. So we could calculate it here, we calculate it here, we could calculate it here. And the way to think about it is, okay, if we're going to represent that electric field, we could do that in a number of different ways. We could represent this in a number of different ways. We could say, okay, I'm going to put a point right here. How big should the field be? I plug it into this formula. Notice the closer it is, the stronger the field is, as it should be. So the stronger field is near this positive charge. And I can represent the size of that field there, calculated using this formula, with an arrow. Okay, so I represent the field at B, at point B here, with an arrow. I can do the same at A, but you can see the size of that arrow is smaller. And that's because this formula will give you a smaller value. Okay, that field is smaller, further away from the positive point charge. Notice they're all pointed away. Why is that? Because the force on a small positive test charge would always be away. So we represent the electric field here as being away from positive point charges. And that makes sense. Notice that is by convention. Okay, so we're not actually putting a small positive test charge here. We're imagining we're doing so and asking what the force per unit charge would be. That's the fundamental question, and that led us to this formula. Notice there's only one Q. That's because there's only one Q producing the field rather than two Qs interacting. Fundamentally, a force is an interaction. It's always double-headed, right? That's Newton's third law, and we'll see that a little bit later. But the electric field is can be due to a single charge alone, okay? And that's what we see here. Now, it's important to recognize that when we represent the field with these purple arrows like so, what we're doing is we're representing the electric field with just a single vector at the specific points that we've shown, in this case A, B, and C. But in truth, a better representation is something like this. This is a kind of representation sort of roughly shown that tries to better represent the fact that this is a vector field, that there is literally a magnitude and a direction calculated with this formula for every point in space around that positive charge. We could do that infinitely. Now, of course, you can't draw infinite arrows, and even if you could, it probably wouldn't be very revealing. So what we do is we draw some arrows, okay? We don't draw all of them, but we draw a lot of them, enough to get a sense of what is happening. And this kind of representation is known as a vector field representation. It's probably the most accurate, although it does leave some out. It's the one I would have you visualize. It is, as it turns out, though, not the easiest to draw and not the easiest to represent. Why? Well, mostly because you have to draw a lot of arrows. Notice we are drawing the same field in this representation and in this representation. It's just that the representation on the left only shows the field at particular points, and the representation in the middle shows the field at a whole bunch of points. Not all of them, because that would be an infinite number of points. Okay, all this space around the positive charge would be filled with arrows, but enough of them to get a sense of the field. Okay, our last representation is by far the most common, but a little bit tricky to use. You always have to be a little bit careful. And in this representation, we use what's called electric field lines. Electric field lines always start on the positive charge and end on negative charges, and they represent what the field would be tangent to the line. Okay, so if I went right here, okay, the direction is shown by the direction of the electric field line arrow, and then the fact that the field lines, you can see the field lines are getting farther and farther apart, that indicates that the electric field strength is decreasing. Notice that that same principle is shown by the fact that these arrows get smaller, and these arrows get smaller as they get further away. That's shown in the electric field line representation just as the electric field lines getting further apart. Okay, so we're going to use all three of these, and you'll get the hang of using them as we sort of do some practice problems and examine some fields. I'm going to pause there, and in our next video, we will take a look at different electric fields. Oh, before I go, actually, there is an example problem here that allows you to practice using this formula. I would encourage you to take a look at it.